Yeah. Okay, so the main goal for today to lay out the proof of the standardization proposition. Which says that there exists for this universal such that any almost contact has C homotopic to C prime, where for finite number of balls, bi subset of M have that C prime is genuine on M take away these balls, and to you have that these are equivalent to these BK universals. All right, and so last time I introduced these semi-regular, semi-contact, regular contact shells. Be adapted that are well adapted to proving this proposition. So just I'll recall what these things are. So you have a disk D2n disk with a function to R they vanish on the boundary with infinite jet. They're positive near the boundary, and then they can be potentially negative inside. So you have V equals 0 with infinity jet on the boundary of the disk near the boundary. And then you define the saucer B to be, say, so D is subset of, D is subset of, right over here, to be W V in D times R such that 0 less than or equal to F. Where F is theta, with f greater than or equal on interior of D and f equal phi near the boundary of D. So it looks like something like this. This is B. And then on each slice foliating B, so on ds, which is equal to V equals S of W, give germ of graph of S of phi subset of D times R. All right, and these are related to these previous B sub k's by this following proposition that basically any semi-contact regular B sub dominates some B sub k, eta sub k, or k. All right, so I'm going to skip the proof of this and just go on to how you can do them. The proof is there's no kind of, the main idea is basically this regularity condition lets you, so just summarize idea. Let's one view phi, so as a map, phi is a map basically from the disk mod its foliation times interval as a time-dependent contact Hamiltonian on this star-shaped domain. So in which, once you have a contact Hamiltonian on star-shaped domain type cross interval, then you're pretty close to considering Hamiltonian on star-shaped domain cross S1. Okay, so but now what I want to start, the main part is how these saucer shapes can be used to start trying to prove proposition 3.1. So the first step is just prove the following proposition. And it's that it's the same, it's proposition 3.1, but now instead of B sub k, you have just some saucers. So up to homotopy, any almost contact has the form it is such that 1, this is genuine on complement of finite number of saucers, and 2 on each saucer is equivalent to semi-contact regular saucer. All right, so any of our almost contact structures, we can homotope it so that the air is a finite number of things. Where it fails to be contact is a finite number of things, and they're all of this form. Okay, so step 1. So this is what I sketched last time. So let this sigma be an S2n subset of M embedded. And by applying Gromov's H principle, we can homotope this almost contact structure to be genuine away from and on near this sphere we have a foliation of germs of contact structures, and is a semi-contact structure on, say, this interval 0 cross 1 cross sigma, which stands in for the region there. So i.e. each is a germ of contact structure on S cross sigma. So it's genuine here, and then on this foliation in between, we have a germ of a genuine contact structure on it. So we have this SCS. All right, so that's fine. So now we want to further regularize this, and we want to say that so regularize the semi-contact structure. So up at step 1, we've reduced our whole problem to what the almost contact structure looks like near sigma. And now we want to further regularize what this semi-contact structure looks like sigma. And eventually we'll be partitioning just this neighborhood of sigma by these shells. So the statement of this that's possible is there exists a smooth function and contact structure mu on sigma times r such that one, this function basically gives you what the contact structure is on each slice, what the germ on each slice is. So you have this is the pullback of mu near S cross where this function of x times s plus t is x s of psi of x plus t. And two, you have closed domains v hat proper subset v subset of M such that psi is positive, related to V is positive, and this contact structure is transverse to the graph of S psi on W hat, which is sigma set minus V hat. So what's the picture of what has happened? So here is here is sigma, here is V, here is V hat. And we have this function that's positive over V. And then once it gets off of V, it might be negative. So this is our function psi. And what's the idea of this proof? So given, say, so you can, by decomposing this interval 0, 1 into small intervals, can assume that assumption number 1 holds. Assume that 1 holds on each little domain. By looking at, by applying Moser to the family of contact germs on S minus epsilon, S plus epsilon. S0, S0. On this, to get them all to be deformations of each other. So then you want to then say how to get, and then so for item 2, you're in a situation where you consider, you break up the situation. Once you are in this situation, you break it up into places where the Reb vector field is very transverse. To the tangent space of sigma cross S, and places where the Reb vector field, and places where mu is transverse to the graph of this function psi, is where this is transverse to, to graph of psi. And applying the Reb flow lets one make this positive away from where the graph is transverse from where the graph psi is transverse to the contact structure. All right, so then step number 3 is that you then bring in these saucers. So we have this picture, so since you know that this function psi is positive on V, one has that this family of germs of contact structures is genuine on V times this interval. So you need saucers where away from V where psi could be negative. Psi could be negative. And how do you build these saucers? Or so what? How do we do this? So let U sub I 1 to n be an open cover biballs of what, of W, which is sigma set minus V. And you pick a partition of unity for this open cover, so let lambda I maps from sigma r to 0, 1. We have support of lambda I contained in UI and with the sum of lambda I restricted to W to be 1. And define L sub k to be the sum of the first lambda i's. And you view these as giving you can use these to view as a partition of sigma across the interval and their graphs. Partition. Sigma across 0, 1. Their graphs, gamma sub LK. So pictorially, you have something like this. So you have, here is cross interval. And together they might, so here's the graph of L1 is this. So this is gamma L1. Then the next subsequent one, you just add a bit more, so it's gamma L2, and could put one more in. So this is gamma L3. Where this, say, this set is this set is R W. All right, and so together the graphs partition. So the region bounded by gamma Li minus 1 and gamma Li. So for instance, starting with this one, then that one, then that one, are saucers B sub I. So this is B sub 1, B sub 2, B sub 3. And so like this, I guess is why being able to do this with your space is why these shapes are well suited. What makes these shapes well suited for this task, because if you just take a partition of unity and the graphs of the functions partition up the space nicely for you. Now, since the graph, so these are since the graph of S psi is transverse to this contact structure, can pick the cover fine enough so that you have that each of these BIs is equivalent to semi-contact regular saucer. So in this is how this is the sketch of how you prove this. So you first just reduce it to the case of some neighborhood around a sphere, and then you you end up looking at this semi-contact structure on a neighborhood of the sphere, and you apply you partition where the semi-contact structure fails to be contact by these bump functions. And on each one of these, you have a saucer that you can prove is equivalent to one of these semi-contact regular saucers.
Sorry,
The complement of V is genuine. So that's what I said here.
So since we're partitioning the complement of V.
Yeah, so on V, it's genuine. Maybe I misspoke. I said the opposite of what you said, and you said the right thing. So on V, it's already genuine.
Okay, and so for item number 2 there,
Yeah.
is that are you saying places where very, very transverse to T?
Yeah.
Places where U is transverse to the graph of psi. Are you saying
V is this
the intersection of 2 sets there? Is that
this whereas tangent space. So so this is V.
and then places where U is transverse to
That's that is that's W hat. So the complement of. So out here, so inside of V, it's the red vector field's transverse. This is basically pointing vertically. That's how you should think of it. And then away from V is where. Okay, so say like you get V hat to be where it's basically vertical. It still stays transverse as you go in V. So by the time you've left V, it's definitely there. The intersections are transverse.
So is that and places where is that?
Yeah, these are. This is place 1 and this is place 2. Is it
the same?
No, they're different.
So the first one is V.
Yeah,
The second one
I guess the complement of V. Or this is probably V hat. And
So the second one is W hat.
yeah, and this is.
And the red vector field being very transverse implies that it's genuine.
So using that the red vector field is transverse, is pointing vertically, you flow by the red vector field to change the graph so that the function becomes positive. Because like, it starts off just here's like the slice and the graph, I don't know, is whatever you want. But within V hat, the red vector field is pointing vertically. So you flow this graph by the red vector field, which is a contactomorphism, so that the graph becomes positive. So after you're done, it's and that's once it's positive, once it's strictly above, that's this condition that the function is positive. And the function being positive means that the semi-contact structure it defines is genuine.
The one pulls back like
Yeah.
step 1.
Yes. All right, so this, we reduced it, our problem now to just, we just have to fill some collection of saucers. And now we need to get to this universal. Hamiltonian. So this is the second part. So for fixed dimension, there exists a finite list of saucers. That can be used to fill any b sub k, eta sub k, for k mapping delta to R. And used to fill is, I'm using this as shorthand for, there's a long statement that you can take any one of these finite number of balls such that it's genuine outside those finite number of balls, and each ball has the form of one of these. Okay, so how do these together? So together prove this proposition 3.1. So it's as follows, that you apply, so take this finite list of saucers, find K universal, such that BK universal, eta K universal is dominated by each of the saucers B sub P, XC sub P in prop 8.1. So one of the first things I said today was that any saucer dominates some B sub k. So each one of these is dominated by some B sub k, dominates some B sub k. So now you have a collection of B sub k's, and you take K universal to be less than all of those. Now you have, now apply whatever this previous proposition, apply prop 6.2 to get MC to be genuine outside a collection of saucers. A finite collection of saucers. Finite number of saucers. Now, yeah.
In this picture, for a source, it doesn't have the almost contact structure have to be genuine along the boundary.
Yes, but it's there along any so your concern is I claimed that the semi-contact structure on this whole thing didn't integrate to a genuine one. That's I've said that, so that's your concern.
Right. Just that it might not be genuine on the boundary.
I claim that still along along the bottom slice, it's along each one of these slices, it's still genuine. It's still a germ of a contact structure. There's no genuine contact structure on this whole picture, but along each slice, I claim there still is a germ.
Okay, but how do you?
It's given.
Take the whole thing where it doesn't work and splitting it up.
But I'm just claiming it works on certain graphs, not that it. On each graph, there's a contact structure. Like on each slice, there's a contact structure given by this map into this picture from sigma. I have a map to R, and I have a contact structure on sigma cross R. So take a thing here, push it forward by the function. Look at that graph. There's a germ on that slice. And that's the thing on the boundary. But since the function's not always positive, these sequence of graphs don't foliate, and hence it's not like this family of germs doesn't integrate into a genuine contact structure. Okay, so to be genuine outside a finite number of saucers, and each of these saucers you have now apply prop 8.1 to replace each saucer with a finite number of saucers B sub P sub to the P from the list. List in proposition 8.1. And finally, this 8.1, once you're only using the ones from the list, you use this B sub K. Finally, fill each B sub P with B sub K universal, eta K universal. Okay, so let me talk about how you prove proposition 8.1. Actually, let me first make a, yeah, so no, let me go to proposition 8.1. All right, so here's the problem we face. So without without this proposition 8.1, we have the following issue. So we can fill each with a collection of B sub k's, eta sub k's, but we have no control on the size of k we need to use. I don't have, so yeah, I have, so the proposition, 6.2 or whatever, gave me a finite, each, given a manifold and given a almost context structure, I get a finite list of saucers. I can fill it up to, I can find some finite number of saucers that fill it. And I know each of those saucers, I can put inside of those some B sub k. But from the get-go, as I, for instance, change the original almost contact structure, I might need to use, the k's might need to become more and more negative, or might become closer and closer to 0 near the boundary. So I might need to use like there's no, the k, like, yeah, there might not, there's, like, it's not clear. There is some B sub k, eta sub k that is dominated by every saucer provided by proposition 6.2. Like it's not, as stated, it just says you can fill it up to some collection of B sub k's, but you don't know what they are. And this is important because we can only use an overtwisted disk to fill B sub k, A sub k, if the disk is defined by some k 0 less than or equal to k. So from the get-go, what we want to do is we want to put in our over-twisted disk defined by some k0, and then run this whole argument and get all that the holes we needed to create are defined by k's where the k is bigger than k sub 0. Like, we can't put the over-twisted disk in after the fact. We need to put it in at the very beginning.
Without 8.1, for each fixed manifold with almost compact structure, you could find something you could use to fill everything, but it wouldn't be the same overall.
No, it's even worse than it's like. So you first put in the over-twisted disk, then you run the argument. And away from this over-twisted disk, you get some collection of b sub k's. But you don't know. First of all, you had to change the almost contact structure to begin with to put in the over-twisted disk. So you don't know what k's you're going to need. And this difficulty doesn't arise in the three-dimensional case because there we have that as soon as the k is somewhere negative, then up to conjugation it can dominate any other one. Because you only need this relation up to conjugation. You don't need it on the nose. Okay, but we have the following kind of saving grace from, I guess, lecture 2 that says that we had this proposition 4.9, which says in motto, the order up to conjugation domination only cares about the region where the function is positive. So, in particular, if you have two functions, one, it's just barely negative, and then positive, then sorry, I might be trying to get this the right way we're going to use it. So it's going to be, yeah, so this, you have this function k, and you have this other function, maybe really negative. K prime. There's not domination, but since K prime is greater than K outside outside this delta prime, you have that BK is dominated by BK prime. So the real issue, so what's the real danger? The real danger is that we might be kicking out so the danger is this proposition 6.2 might kick out some B sub k's, A sub k's, where the negative, where the positive part, positive region of K mapping delta cylinder to R gets arbitrarily small. So you're never going to be able to find something since this K prime, you're going to have to get this K prime to be, the positive part to be arbitrarily small. It's going to be hard to get a single K that's less than all of them, even on the positive part. So that's where the following idea, so the following idea is in just the interval, but it gives the idea of how to get around this issue. So example. Behind the proof of prop 8.1. So I'm going to show that a single function and its translates, you can add them together to get a function whose negative region is a large part of the whole space where the function is defined, i.e., so consider phi is the map from R to R, and it's this. So from 0 to 1, it's just 1. Put it in color. From 1 to 2, it's down here, and then it's back up here again. So -3. So this is the size of this one function, the size of its, where it's positive is relatively large to, well, it's controlled to the region where it's negative. But you can, using this function and translates of it, you can consider f sub k, which is the sum of compose j for j equals 0 to k, where j of x is x plus j. X minus j. Okay, so in this function now is it's like this, and then the next term is at The next term goes to -2. Then the next term's then it's at -1 for a while. Then it's at -2. Then it's back up to 1. So whatever those are, is k plus 2, k plus 1. So what this example shows that fk, whose positive region divided by negative region is going to 0 as k goes to infinity, is just phi is just a sum of phi and its translates. So the issue of the positive part of the region becoming arbitrarily small, this example hopes that, well, up to some finite list of functions, you can add these functions together with their translates to get it to be, you might get being kicked out things that's arbitrarily small, but those things that are becoming arbitrarily small, in turn, can be written in terms of things with fixed sizes. So the question is, what plays the role of now? How does this example generalize in higher dimensions? So for this standard, plus minus yn dxn. All right, so there's for just n equals 0, we just had translations, but you can form the group generated by these translations into this higher dimensional generalization. So you have, consider the subgroup of Kant R2n plus 1 generated by kind of TZ, which is just maps Z to Z plus 1, TXN, which maps XN to XN plus 1. So you have some translations and you have some shears. So you have S, Y, J, which maps. So it's only going to act on. I'm just writing the variables that it acts on. It acts by the identity on all the other variables I don't write. It maps yj z to yj plus 1 comma z plus xj and s. xj maps xj and z to xj plus 1 z minus yj. And so this is for j equals 1. That's 1. So this is all these commute, except everything commutes. Except the commutator of s of yj and s xj is this. So hence, so everything in this is writable as just a word, like as a standard presentation. And using that everything can be written this way, you see that this group acts properly discontinuously on the slice yn equals 0. So you have that this group preserves the plane yn equals 0 and acts properly discontinuously. So, i.e. that if you have some compact subset, then S of Q, which is defined to be the G's, such that G of Q intersect Q does not equal the empty set, is finite. And it's ultimately the finite list that we're going to get is ultimately going to be determined by what the geometry of these intersections look like. So pick Q subset of this such that its orbit under equals. So such that you get the whole thing. So an example is just given by the unit cube. unit cube. All right, so at this point, I can write out formulas, but let me just say that I'll write down a function. So consider the function. So enumerate this group and pick a function on Q that looks like this, where the negative, the min of phi is less than it's less than, so where this part, little m, where it's constant, so where little m is less than, say, the size of S of Q plus 1 times the max of phi. So this is just the kind of the analog. This condition is the analog of that I picked 3 here based on how the intersections of these intervals, how the intersections of these domains behave under translation. So you define a saucer, find saucers b sub k to be phi k minus 1 less than or equal to y sub n less than or equal to phi k, subset of R, where phi sub k is equal to the sum of equal to max plus the sum of phi composed g sub j inverse for j equals 1 to k. So these are some collection of saucers. And lemma up to equivalence. There are only 2 to the size of this set different saucers. Yn is the coordinate on this R. And why do you see this? So we'll just look at as k. So this, sorry, what I wrote was slightly wrong. This is not that. It's on g sub k of q cross r. All right, so it's just the proof is you just translate them all back to be sitting over Q. So look at Vk composed G of k as a map from Q to R. And you have that, what is this equal to? This is equal to this max V plus some V composed Gj inverse Gk restricted to Q. J equals 1 to K. And so this, a summand is only going to contribute. This, a summand, only contributes when G, J, G, Gk of, I'll just write when Gj, Gk inverse of Q intersects Q. That's phi is only defined, phi is supported inside of Q. So it's just, and this is only, there's only a finite number of such j's, because that's, from the get-go, we assumed finite number, i.e. this size of this set S of Q. So most of these sums are 0, but finite number of them are going to be non-zero, and then so the equivalence class is just what subset of these terms are, of what subset of SQ elements are non-zero. All right, so then kind of, I'll just say so for the proof of this proposition 8.1, you show that given this function defining b sub k can get finite subset of this lattice with and delta prime subset of this with k restricted to delta prime, the complement. And you have that phi delta n, which is max over n plus some phi imposed G inverse you have this function with where Cn of, this is just a scaling contactomorphism. So you can have this function with C less than or equal to K near the boundary, and phi lambda n to be less than 0 on delta prime. So the picture is you have this given function k, and it's like this. So you can apply this proposition to get that B of phi n is dominated by this B sub k. But by design, you have this function here is, and B sub gamma n decomposes into one of our finite, decomposes into the saucers. B sub bad notation. Whatever these things. Into the saucers for k coming from list of 2 to the size of this SQ saucers. So these different equivalence classes defined by this are a finite list in the statement. And by adding them together, you can get functions like this that the positive part is controlled to get domination. And so that's the proof of that. And I think that's it.
when I take a ball and I do comma outside,
Yeah.
I can extend it in the given class.
Yeah.
Okay.
Sorry.
I mean, after you prove this result, I know that I can.
Yeah, inside a ball.
Yeah.
Yeah.
That gets rather technical.
Yeah. I'm sorry.
Yes.
So is the twisted disk explicit?
The size of it, like with the first lecture, I gave an explicit function. I just don't know how. What's not explicit is how negative it needs to be, or like how small the positive part has to be. That's what's not explicit. And if you wanted to find what was explicit, you would have to unpack. You'd have to pick a Q, look at these intersections, like pick your function phi appropriately, and see what popped out there, and see what k, how small k you need to be smaller than this finite list of saucers you get here. So you need to find some overtwisted disk defined by a k that is dominated by each one of these things in the list, if you wanted to make it explicit.
So you probably could. I don't know if that's any.
Yeah, it's not, the axiom of choice wasn't used like in an essential way.
Any other question? Okay, let's thank our speaker for